So last class we talked about percentiles and even quartiles and how distribution of the data and stuff like that can be approximated with the interquartile range. Today we want to get into the topic that really kind of starts to tie it all together, and that's probability. Probability is flat out just how likely it is something will happen. Probably the simplest example of this is flipping a coin. So for probability to be used, there has to be an event that we're trying to analyze or predict. So here the event would be flipping a coin. Manufacturing that event would be testing a part. And flipping the coin, we want to know there's outcomes or results of that event. And we want to know how likely it is that each of the possible results will occur. Well, there are two possible results here. Now, someone might say, well, what if the coin lands on its edge? Well, that's like a 1 in 20 million chance. If you have enough time in your life that you can flip a coin enough that you actually get one to land on its edge, I'll give you an A in the course and never talk to you again. Okay? You got 3 days to make it happen, and you have to videotape it. I mean, it is something you could get 1,000 people in a room and have them flip a coin for the rest of their life, and maybe 1 or 2 of them will have it actually land on its edge. It's not likely enough to make it worth analyzing. But heads, well, we'd expect 50%. Tails, about 50%. So we either express the probability as a percent, we express it as a decimal, 0.5 and 0.5, or we could express it as a fraction, 1/2 and 1/2. It's actually this fraction that makes the most sense, because in that fraction form, it actually describes how we found that probability. Because the 1/2, the 1/2 is actually describing the outcomes. The 1 represents the desired outcomes. For heads, it's getting ahead. The 2 represents the total outcomes. There are 2 total outcomes. One of them is our desired outcome, so it's 1 out of 2 chance, or 1/2 probability. Now, this is describing, of course, a fair coin. In the US, we do not necessarily mint fair coins. If you do it, like the state quarters and stuff, there have actually been studies done. There's a lot of people with spare time on their hands. You take the state quarters and you flip them about 2,000 or 3,000 times. They will not come out. Let's say you do it 2,000 times. They will not come out to 1,000 heads and 1,000 tails. They will almost always come out slightly greater one than the other. And it's not that, I mean, there's random chance that comes in there. We'll talk about that a little bit. But they actually are slightly unbalanced. So it depends. And actually, each different state quarter has a different probability of heads and tails. Most of them are slightly more likely to come up heads than they are tails because of the way they're shaped. The tail side of the coin is slightly flatter than the head side because of all the different engraving in it. So when it hits the head side, it's more likely to bounce back over to the other side than it is the other way around. But there is something called random chance. If you flip that coin, a 1,000 times, you would expect 500 heads and 500 tails. The chances that you get exactly 500 heads and 500 tails are very slim because it's random chance or random variation. if you keep flipping and flipping and flipping, it's going to get closer and closer and closer to 50-50. But, there is still randomness involved. It's going to be, even though it's a 50-50 shot, each time you flip it, there's always that chance. You might get 7 or 8 in a row that are all heads. I mean, it's still possible with the random variation. So at the end of 1,000 flips, have exactly 500 and 500 is very unlikely because of those random variations. Because of that, let's say you have a population of parts. You have 1,000 parts. Out of those 1,000 parts, 10 are bad, 10 are unacceptable, 990 are good. Let's say you are going to take a sample of 50 to test. 50 is about 1 out of every 20. About 1 out of every 20, what we're seeing here is 1% are bad, right? That 10 that are bad, that's 1%. 99% are good. A representative sample. Remember, we used that word before. What's that mean? A representative sample means the sample statistics are about the same as the population parameters, where all proportions or percents are the same. If 1% of the population is bad, we'd expect 1% of the sample to be bad. 1% of 50 is 0.5, or 1/2 of a part. So we would expect in a representative sample to have 0 or 1 bad parts. Does that make sense? What's that? Well, and that's where that random variation comes in. It is possible, even if you use random selection, it is possible that out of those 20 parts, you might have, or sorry, out of those 50 parts, that sample 50, you might have 5 bad ones and 45 good. Well, that comes down to 10% bad. So it's possible, even though you use a good random process, that you just randomly select a bad sample. So what we do is we're looking for what is the probability. If that is true, so we assume that only 1% of our parts are bad. So if we assume that 1% of our parts are bad, what is the chance what's the probability that we might actually select 5 bad parts out of 50 for that sample? Well, it's probably pretty low. I could actually do the probabilities for you, but I don't want to. That would be a huge jump right now. To select a certain number of bad ones. Each one, the probability of selecting a bad one for each one, well, there's 10 bad parts out of 1,000, right? So that's 0.01. So the probability of randomly selecting a bad part is 1%, because 1% of them will be bad. So the probability of selecting 5 out of 50, again, that's a complex probability. If we had another week or so, we would get into that. That would be considered a binomial probability. So that's a bad part. Let me show you how that would work. I'm just going to use the calculator to do it. So binomial probability is down my list a little bit. Option A is binomial PDF. How many trials are we selecting 50 items? What's the probability? 0.01. X value is how many of them do we want? We want 5 of those bad ones. So the probability of randomly selecting 5 bad ones, that is scientific notation. That -4 is actually 10 to the -4th. This is 1.35 times 10 to the -4th. So that 10 to the -4th means the decimal point has to move 3 or 4 spots that way. So that is the probability of randomly selecting a sample with 5 bad parts out of 50 if only 1% are bad. That's very, very, very unlikely. That's less than that's about 1/100th of a percent, or a 1 out of 10,000 shot. That's pretty unlikely. So what does that mean? There's the law of unlikely events. Most of the time in manufacturing, unlikely means less than 5% chance. If we assume something, here we assumed that 1% of the parts were bad, that only 1% of the parts were bad. If we assume something and then make an observation, here our observation was we selected 5 bad parts out of 50. And if the chances of that observation occurring are extremely unlikely based on our assumption, then the assumption must be wrong. So I'm going to go through that again. That's a very important process. We make an assumption. We assume that only 1% of our parts are bad. Then we make an observation. That's where we selected the sample. The observation was 5 out of 50 were bad. The probability of the observation if the assumption were true is very, by very I mean less than that 1 in 10,000 we saw up there, unlikely. So then we assume the assumption is wrong. That actually is a big deal in manufacturing. So we make the assumption that our process is in control, it's producing good parts. But then when we get a sample of parts that we've tested that would be very unlikely, given that the process is actually working well, then we have to assume there's something wrong with the process. That's where we shut things down and take a closer look. And again, there's a fine line there as well. Sometimes if it's bad enough, we shut things down until we figure it out. Other times, if it's not like disastrous, we will keep running, but just start doing more intense quality control inspections. Rather than testing every 50th part, you might test every 20th part coming off the line to see if you can nail down really what's wrong. Okay, so anyway, let's say you want to roll a die. Can you tell me what is the probability of rolling a 4? 1 out of 6. You had it backwards there. It's always the The desired ones over the total. 1 out of 6. You're thinking odds, not probability. Odds are what they give you at the the racetrack. There's no gambling in quality control. Let's say we're going to put some marbles in a box. I'm going to put in 30 blue, 20 red. What is the probability of reaching into the box and grabbing out a red marble? 20 out of 50, or 0.4. What is the probability of reaching into that box and grabbing out a blue marble? 30 out of 50, or 0.6. Now, what is the probability of reaching into that box, grabbing a red marble, and then another red marble? Well, the answer is there's not enough information. There's two possibilities here, with replacement or without replacement. It is a technical term, but it actually means exactly what it sounds like. I'm drawing out two marbles here. The first marble, the probability that first marble will be red is 20 out of 50, correct? But before I draw the second marble, I need to know if I put the first marble back. With replacement means I put the first marble back in, I mix them up again, and then I draw it out. If the first marble is red and I put it back, what's the probability the second marble will be red? Still 20 out of 50. So that ends up being 400 out of 2,500, or 0.16. Without replacement, the probability of that first one being red is 20 out of 50. Without replacement means I look at it, I see it's red, and I throw it away. What's the probability of the second one being red? There you go, 19 out of 49. So that ends up being 380 out of 2,450. So 1.1551. So you can see it's slightly more likely, or slightly less likely if we don't replace them. With replacement, it's called independent. The probability of drawing a red marble never changes. It doesn't matter what the first marble was because we put it back and we mix them back up. So the probability of that second marble being red will always be 20 out of 50, no matter what the first marble be. This, of course, here is dependent. Because since I'm not putting it back, the probability of the second marble being red depends on whether the first one was red. Now here we only considered that the first one was red because we wanted both of them red. If the first one wasn't red, we would have stopped and we don't even care about the second. But the second marble being red depends on what the first one was. If the first one was red, well then the second one, 19 out of 49. If the first one was blue, the second one being red would be 20 out of 49. So the probability of that second marble being red depends, it's dependent on whether the first marble was red or blue. This is a fairly simple concept, but the application can get pretty complex. In manufacturing, when you're testing parts, is the probability of a part being bad independent? Well, if the process is under control, what does under control mean? That means we have controlled every variable that we possibly can. That does not mean there's no variation. There's still random variation. But all the causation that we can control. So there's common cause and or assignable cause, and there's common cause variation. Assignable cause is stuff that we can find its cause and we can eliminate it. Common cause is just variation that's always there. If it's under control, yes, the probability of one part being bad is independent of the other one. If one part is bad, the next part could be good or bad, depending on random variation. If it's not under control, then no. If one part is bad, that increases the chances of the next part being bad. And that's what we're looking for when we're looking at quality control. Can we see when it's predictable? If having one bad part does not help us predict whether the next part is bad, that's actually a good thing. Does that make any sense? One part being bad is just a random variation. The next part could be good or bad. If one part is bad, helps us predict that the next part's probably going to be bad too, that's a bad thing, because then there's a predictable pattern, which means there's something wrong with the process. It's not just random variation anymore. There's a lot more I could say about probability, but we're going to put that aside for now. I want to talk about normal probabilities. We saw that bell curve thing a couple of classes ago. We said the center of that's our mean or median, and the width of it is the spread, is the standard deviation. Let's take a look at how that actually fits together. I'm going to draw this curve a little bit bigger. So we said the center of that curve is the center of our data. I want to just take a quick peek just to make sure that I'm using the same percents that they are. See if they did use any percents, to be honest. I'm not seeing any that they've used. Okay, so they didn't really put the percents in here. So I'm going to use the ones that I'm familiar with. So the center of this curve is the mean. Then we go out 3 steps in either direction. The step is a standard deviation. So going to the right, this here is +1 standard deviation, and I'll talk about what that means in a minute. This will be +2 standard deviations, +3 standard deviations. Going to the left, that's -1 standard deviations, -2 standard deviations, -3 standard deviations. What does that mean? Well, let's say that we have a part that when we test it, the mean strength is it'll hold 1,200 pounds without breaking. And the standard deviation, is 40 pounds before it breaks. What does that mean? Well, that means that when you test parts, not all of them are going to be right at 1,200 pounds. Some are going to be a little less, some are going to be a little bit more. That's what the standard deviation means. What this bell curve is saying is the very center of the bell curve is 1,200 pounds. Each step is a standard deviation, so that's 40 pounds. So this is 1,240 pounds, 1,280 pounds, 1,320 pounds. Going this way, subtracting 40 pounds at a step is 1,160, 1,120, and 1,080. Well, what do those tell us? Well, there are percents in this curve that are always there. These numbers that I just put in, they change depending on what the mean and standard deviation are for the set you're working with. So for this set of parts, we measured the parts, and we got that the mean strength was 1,200 pounds, and we calculated the standard deviation at 40 pounds apart. In any set, no matter what the mean and standard deviation are, 34% will fall between the mean and the standard deviation on either side. So 68% total between the standard deviations. 13.5% will be between 1 and 2 standard deviations on either side. 2.35% between 2 and 3, and 0.15% outside of 3 standard deviations on one side, on each side. What that is saying is if you add up these percents from here to here, that 95% of parts will fall in that range. Always. Now that's a very important thing. From here to here, from here to here, that's 99.7%. That's 997 out of 1,000 parts. So what does that mean? Well, that means that we test a part. It breaks at 1,291 pounds. Where does that fall? Between 1,280 and 1,320, right? It falls somewhere in here. Well, we'd expect 95% of the parts to be inside there. Less than 5% would be outside that range. Is that an unusual event? Yes, it is. Now, is that a bad thing here? That's stronger than we want it to be, right? So does that mean we shut down the line and figure out what the heck's going wrong? No. Well, if it's a shear pin that has to break under in a safety situation, yeah, that could be a bad thing. If it's not, if it's a part that needs to hold that stress and it's a durable part, well then being extra strong is a good thing. Does that mean we just ignore it? Well, no. That's one of the things in statistical process control. Everybody thinks that it is to keep us from making bad parts, and that is one of its main purposes. That if we start making bad parts, we stop and we figure out why they're bad. But also, statistical process control is a tool for improvement. If we start making parts that are better than normal, like this one, we want to figure out why that one turned out better than normal so that we can repeat it and keep doing it. Now, it may be that something happened in the mold and the part got molded extra thick. Okay, well then, that might not be something we want to continue because we don't want to put the extra money into the extra materials. But at least we want to identify why that one came out stronger than the rest so that we can repeat it if we want to. Or if it's something that's costing us extra money, like the extra materials, we can stop it from being expensive. But again, this is in that 5% range. From here out, right in here is where it fell. What if we produced a part that breaks at 1,072 pounds? That's out here, isn't it? That's outside of the 99.7%. That's in that 0.3% range. That's usually an immediate flag. If you're outside of this range here, the 3 standard deviations, that's an immediate flag, and a lot of times you will shut down the process quick for a quick test. Or if you don't shut it down, you'll grab another handful of parts and test them right away just to make sure. Because the chance is 3 in 1,000. If the process is performing correctly, there's less than a 3 in 1,000 chance of producing a part that far out. Well, then you select a couple more parts off the line. If any of those next 5 or 10 parts are bad, are in that same slot, you know that there's something wrong, because there's no way you could produce 2 parts in that range in a short period of time and still have the process actually under these conditions. That means that the mean is somehow changed. Something has changed in your process. If it's just in this range here, that what we call the 95% or 5% range, which is where our first one was, well, then we would keep testing. If we have more than a couple parts in the next 5 that fall outside that range, then we may want to look closer. So it's all about probabilities. This here, having one part outside of the 3 standard deviation range, that's unlikely enough that we're going to go ahead and check it out just to be sure. Having a part outside of here, that's unlikely, but it's in that 5% range. we're not going to worry, we're not going to get too excited about it. We're going to watch it closer. We're not going to get too excited about it until we have several that are outside of that range. And then we, okay, having multiple items outside that range, then we know that's very unlikely. How would we know how unlikely it is? Well, let's say 2 in a row. It's 0.5 is the chance, 0.05, I should say, 5% is the chances of one of them happening, right? 2 in a row would be 0.05 times 0.05, that's 0.0025. Less than 1/4%, or about 1/4%. So that's very unlikely. So that means, okay, we can go back and say, 2 in a row outside that 5% range is just as bad as 1 outside of the 3 standard deviation range. Does that make sense? So these percents right here never change. Depending on what textbook you're looking at, they might be rounded a little bit differently. Some textbooks round this instead of the 34, they round like 34.27 or something like that. They're rounded a little differently. I use these numbers because these are the ones I've memorized through the years, and they've been rounded off slightly. But those percents are pretty much the same no matter what. What changes are these numbers here, depending on what you're looking at, your mean and standard deviation. Let's look at an application maybe in your everyday life. Let's say you get a job offer and you're looking to move and you want to buy a house. You want a 3-bedroom, 2-bathroom house. You do your research in the area you're moving into. Over the last few years, the sale prices of houses that are 3-bedroom, 2-bath have a mean of 142,000 and a standard deviation of 19,000. So what does that mean? In this curve, the center number here is 142,000. I'm just going to write it as 142. If I go this direction, each step is 19,000, the standard deviation. This is 161, 180, 199. Going this direction, each step is standard deviation, 19,000. So this is 123, 104, and 85. These percents, however, are still the same. So let's say you're looking at houses and you find one you absolutely love. It's just beautiful. And the sale price is 180,000. Your agent is telling you better put in an offer for this house right now. You're never going to find one this nice for that price. It's going to sell fast. Well, the numbers here tell us 180,000 is right there. If I want to know what 1% of houses in that area cost more than that, what would I do? The left side or the right side? Right side is more than 180,000. I add those percents up, that's 2.5%. So of the 3-bedroom, 2-bathroom houses in that area that have sold, only 2.5% have sold for more than that. What does that mean for the percent that sold for less? If I add those all up, that's 97.5%. In that area of all 3-bedroom, 2-bathroom houses, 97.5% were cheaper than that. So what does that tell you? Well, it tells you, one, either that seller will probably take less for that house, or you're going to find a house that's 3-bedroom, 2-bath that you still like that's a lot cheaper than that one. Does that make sense? So that's what those numbers come into. Now, when you guys talk about control charts, what happens on those control charts is we turn this curve sideways. The bell curve looks like that. And you talk about upper control limits and lower control limits. Have you talked about that at all when you guys did it? So your upper control limit here is usually the +2 standard deviations. Your lower control limit is usually down here at -2 standard deviations. And then you have an absolute limit is out there at +3 and -3. If you have even one point that's outside of the 3 standard deviation limit, that usually tells you you're out of control. We discussed if you have 2 in a row that are outside of the 2 standard deviation limit, and some process control is kind of a by feel thing. It's not necessarily hard and fast rules. Some will say that if you have 3 out of 5 that are outside of that 2 standard deviation limit, you still want to check it out. Others will say 2 out of 3. So it all depends on what your standards are and stuff for quality and whatever. For now, I'm going to give you some homework out of the big book. I'm going to have you do page 684. Exercise 32-1 and page 686, exercise 32-2.